Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Host Omar Sayed from University of Pennsylvania today. And this is joint work with Rob Schapire, computing mistake, exploiting optimal strategies in very large zero-sum games. Thanks.
Okay, well, thanks for inviting me. It's a pleasure to be here. As Ofer said, today I'll be talking about computing a certain kind of optimal strategies in really large games. This is joint work with my former advisor at Princeton, Rob Schapire. I graduated from there about a year and a half ago, a little bit more than that, but I've continued to work with him, and today I'm going to be describing sort of recent work that we've been collaborating on together. Okay, so I'll be talking about zero-sum games today. So a zero-sum game is a strategic interaction between two autonomous agents who have diametrically opposed goals. Sort of the usual and canonical example of a simple zero-sum game is the children's game rock, paper, scissors. In rock, paper, scissors, each player has 3 strategies, and they have this sort of cyclic relationship. So rock breaks scissors, scissors cuts paper, and paper covers rock. So because of the cyclic nature between the strategies, or among the strategies, there's no single strategy that is guaranteed to win for any player. So this raises the question of, well, how do we define an optimal strategy? So in zero-sum games typically, and really in the study of game theory more generally, people usually define optimal strategies in a worst-case kind of way. So the best strategy in a zero-sum game is typically defined to be one that is best in assuming a perfectly adversarial opponent. That is, choose the strategy that is going to do the best assuming the opponent plays the worst counter strategy. So in rock, paper, scissors, if you've ever played it as a child, the best thing to do is just randomly choose one of the 3 moves. And even if your opponent knows that you're doing that, this strategy is guaranteed to get a draw on average, and no strategy can be guaranteed to do better. So therefore, it's optimal. Now, you might think that planning for the worst case is a really sort of safe and conservative approach. And you might wonder, well, if I plan for the worst case, does that mean that I'm going to be optimal in every case? And the answer is no. You may actually fail to exploit, by assuming that your opponent is perfectly adversarial, you may have failed to exploit a mistake by your opponent. So let me try to extend this simple example to try to illustrate what I mean. So let's extend the game a little bit, and let's consider the game rock, paper, scissors, bomb. So this is an asymmetric game. So let's say one of the players, player 1, has a move called bomb. And bomb has the property that it beats everything. So obviously in this game, the optimal strategy for player 1 is bomb, naturally. And now what's interesting is that using our worst case definition of optimality, every strategy for player 2 is optimal, because every strategy is sure to lose if you assume that player 1 is going to play the best counter strategy. But what if player 1 makes a mistake? What if he forgets to play bomb? What if he doesn't know that he has a bomb? So in this case, the best strategy if the player 1 forgets to play bomb would again be the uniform distribution on all 3 moves. But nothing in our current definition of optimality is guiding us towards that strategy. To give you a slightly less trivial example, this position in chess is called the Saavedra position. So here we have the black player and the white player. The white player has a king and a pawn, and the black player has a king and a rook. And if you play chess, you know that a rook is much more powerful than a pawn. And so it would appear that in this position, this is a sure win for black. Black seems to have an enormous advantage. And indeed, for many, many years in the 19th century, people assumed that this position was a win for black. But then in 1895, this Spanish priest named Reverend Saavedra, and I'm not sure if I'm saying that right, if anyone speaks Spanish, correct me, discovered sort of an ingenious sequence of moves that actually wins this position for white. So imagine now you're the black player, and you find yourself in this position.
Who has the next move?
White to play. So white to play and win. And white is going towards the top of the board. So he can't kill the rook right away. So if you're the black player in this situation, you find yourself in this Saavedra position, and you're a very good black player, then you know that once you've reached this position, the game is a sure loss, assuming your opponent is perfectly adversarial. And so now, from this position, you would regard every possible sequence of moves as equally good, that is equally bad, because they all lead to a loss. But if your opponent, the white player, doesn't know about the Saavedra position or fails to properly execute the ingenious sequence of moves that leads to a win, then you should exploit that. But again, our current pessimistic definition of optimality isn't guiding us towards any strategy like that. There's when I was reading about this, there's a chess grandmaster named, I think, Fred Mitchell, and he has a saying that the hardest thing to win in chess is a one game. That is, the hardest thing to do is that once you've reached a position that is known to be a win, it's actually very hard to execute that all the way through to completion. So in this talk, I'm going to be talking about how to efficiently compute mistake-exploiting optimal strategies in really large zero-sum games. And that'll be the bulk of the talk. And then towards the end, I'll try to connect this more to machine learning and specifically reinforcement learning, which is an interest of mine, and show how the algorithm we develop for computing these mistake-exploiting strategies can be used to solve certain problems in reinforcement learning. But that'll just be a little bit at the end of the talk. Okay, so here's kind of a roadmap. So let me sort of more formally define what exactly is a zero-sum game. So every zero-sum game is defined by a matrix called the game matrix. And there are two players called the row player and the column player. And the game proceeds as follows. The row player chooses a distribution on the rows of the matrix. The column player chooses a distribution Q on the columns of the matrix. And the payoff of the game is just the expected value of an entry of the matrix with respect to the row and column distribution that the two players selected. And that's the end of the game. These distributions are called strategies. And a degenerate distribution that's just concentrated on one row or one column is called a pure strategy. So for rock, paper, scissors, the three pure strategies were rock, paper, and scissors for each player. So we need, they have diametrically opposed goals, so we just need to assign some sort of polarity to each player. So we say that the row player is the minimizing player. He wants to minimize the expected payoff. And the column player is the maximizing player. He wants to maximize the expected payoff. And then those worst case optimal strategies now have the following definition. So for the row player, his optimal strategy is the minimax strategy. That is the row strategy that minimizes the expected payoff for the worst case choice of the column distribution. And the best strategy for the column player is just the sort of reverse definition, the Maximin strategy. The best column distribution for the worst case row distribution. Okay, so that's the traditional definition of optimal strategies. Now I want to define some notion of a mistake-exploiting optimal strategy. Now there's more than one way to define such a thing. I'm going to choose a certain definition, and I'm going to try to motivate it as follows. So let's look at the game from the perspective of the column player. So his Maximin strategy is the strategy Q that satisfies this objective. And another way of looking at this objective is saying, okay, I want to choose a column distribution Q so that the column vector MQ has the largest minimum row, right? When I hit M with this column distribution, I'm now basically presenting the row player with this column vector of choices, and they each have some expected payoff. And now the row player, if he's maximally adversarial, there's a best choice for him that's just concentrated on a single row. And so all I'm doing is saying, okay, of those choices the row player now has, I'm trying to maximize the smallest one of them. And if the row player makes a mistake, one way we can think of a mistake is failing to choose that minimizing row. And if he fails to choose that, he'll choose some other row. And what's interesting is that our current objective doesn't care about the values of the other rows. And so maybe we should modify our objective so that not only does it try to maximize the minimum row, but maybe something about all of those rows. And so this discussion suggests the following definition of a mistake-exploiting optimal strategy. So it is the strategy Q that for this column vector MQ maximizes the minimum element of that vector. And among all such column strategies, maximizes the second smallest element. And among all such column strategies, maximizes the third, and so on. So in other words, it's trying to increase these things lexicographically.
That I get it right. So it doesn't mean it could be that if my opponent, if I know the strategy of my opponent, I could have done much better than that.
Definitely.
Right. Yeah. But you're still being conservative in the sense I want to guarantee the minimal payoff as in the classical game theory.
That's right.
But
okay. That's right. That's right. So this is a special case of a Maximin strategy.
Is this willing to pay off a little bit and get not quite optimal smallest row to get a better second smallest row? Or
This definition is not willing to do that.
How do you define the smallest, the second smallest, third smallest, all maximize? I guess sometimes they're conflicting, right? For example, if you want to max the smallest, it has to be these three are dependent.
Yeah, that's right. Yeah, you're right.
You're right. Have a definition.
There may be no strategy that maximizes all rows simultaneously. So the definition is the following. I look at the set of strategies, column strategies that maximize the smallest value of the row, maximize the minimum row value. This is some set. Now I look in that set, and I ask which of them maximize the second smallest row value. Now I have a smaller set, and then I just recurse. Okay. And a shorter way of saying that is I find. Well, let me give the more formal definition. So the formal definition of what I just said is we define the column player's lexicographic Maximin strategy to be the strategy here that. Okay, so what is this sort of saying? Here's MQ, that row vector, that column vector I was talking about. This theta is a function I'm just going to define that just sorts the elements of this column vector in non-decreasing order. And this lexmax operator is just this is the maximum with respect to lexicographic order. Okay, so I hope that's clear what's going on. Meaning, first of all, the component 1 should be as large as possible. So, two vectors, dictionary order. So compare two vectors, component by component, starting with the first one. And the first place where they differ, the smaller component is the smaller vector.
Suppose to make the first one smallest, then actually Q has a unique solution.
I beg your pardon?
Suppose there's a unique solution Q that makes that one smaller.
Then this is sort of degenerate. Then the maximum.
Because if you want to make any change to accommodate the second one, you have to change the first one.
Yeah.
It's kind of
yeah. No, it could happen that
if you have a single optimal strategy in the classical sense, then
it is also the lexicographic optimal strategy. That's correct.
We're just trying to understand. So in the setting, for example, of the plain vanilla rock, paper, scissor, actually, you have just the one optimal strategy, and
that's right. That's right. But in rock, paper,
when you hit the bomb, then it becomes more interesting.
That's right. And anytime you have two pure strategies that are both Maximin, then any linear or any convex combination of them is also Maximin. Yeah. And so then in that setting you have infinitely many optimal strategies.
But you're not guaranteed. So could it be that in the case that there are many optimal strategies in the classical sense, could it be also that they also match in all properties in all higher order?
It could happen.
It could happen.
Yes. There could be a pure strategy that is also lexicographically optimal. It can certainly happen.
I guess another way is idea is you could define a distribution on, for example, the outcome on the first, the second, the third one. So you use a convex combination. You want to maximize the convex combination of the first, the second, the third one.
You could, yeah. That sounds like it would require some kind of prior knowledge about how your opponent is going to behave. Yeah. And if you had this prior knowledge, you could certainly exploit it. But in this setting, we assume we don't have any kind of prior knowledge, and we're trying to take sort of the usual conservative game theoretic approach, but refining it somewhat. Is there? Okay. So let me give you some history. So we didn't invent the idea of lexicographic optimal strategies. They were first introduced by Melvin Dresher way back in 1961. He didn't give them a name, so if you look at the literature, people just call them Dresher optimal or d-optimal strategies. And what's interesting about them is that people have made connections between these and other notions of equilibria in game theory. So today I'm just going to be talking about zero-sum games. More generally, there are general sum games. And in a general sum game, there's this concept called a Nash equilibrium that you are probably familiar with, which is a situation where every player is playing a strategy and no player has any incentive to deviate from that strategy. And something that people have studied a lot about Nash equilibria are refinements of the equilibria that are sort of less sensitive to perturbations. So it turns out that some Nash equilibria in some games are really sensitive to perturbations, meaning that if one person slightly changes their strategy, then it's suddenly not Nash at all. And so people are interested in strategies that are Nash equilibria that are not just Nash, but also insensitive to small perturbations. And there's a whole menagerie of refined equilibrium concepts in general sum games that correspond to different definitions of perturbations. But in zero sum games, everything sort of collapses. All of these refinements all coincide with lexicographic optimal strategies in a zero sum game. So, so if both players in the game are playing a lexicographic optimal strategy, that's a proper equilibrium, that's also a perfect equilibrium, and there's a few other things it is. Okay, so having defined and hopefully motivated this solution concept, let's turn to trying to compute it. Throughout the talk, I'm going to be looking at the game primarily from the perspective of the column player, but most of what I say can be applied to the row player as well. You just turn everything around. So if you wanted to compute the classical Maximin column strategy, you could do it just by solving this objective. The linearity of this problem, you can see directly that you can solve it by solving a linear program. You can compute this Q star. And the size of that linear program is roughly the size of the game matrix. And so you can find this strategy in polynomial time in the game matrix, in the size of the game matrix. And do we have a solution like that for the lexicographic optimal strategy? And indeed we do. So Milterson and Sorensen back in 2006 described a very similar approach to computing these lexicographic optimal strategies using a sequence of linear programs. And the way that their algorithm works is as follows. So the first algorithm in the sequence outputs a set of linear constraints. And these linear constraints define the set of optimal strategies in the classical sense. Then those constraints are fed to the second linear program in the sequence. And that second linear program uses it to find strategies that are optimal on both the minimum and second smallest row. And it outputs a set of constraints that describes that set. And then each successive stage does better on the kth stage figures out the kth row, and by the time you're done, you've found the lexicographic optimal strategy. And since you have to solve one linear program per row of the matrix, the time of this entire procedure is polynomial in the size of the matrix. So that's fine. But a setting that we're interested in, and I'll be talking about today, is when one of the players has a very large number of strategies, exponential, maybe even infinite. And so the game matrix looks like this. It's much wider than it is tall.
Sorry, can I just ask a question about this other algorithm?
Sure.
So you're saying that the output of each one of these LPs is a set of constraints?
Yeah.
So basically what this would be the constraints that have non-zero dual variables? It has to be some sort of duality. That's what it is? I mean, if you have like linear programming algorithm will give you an answer which is just a point inside the constraint set.
Right.
But you're looking at this, you're asking what is this, you want the entire set of all feasible.
Yeah. So let me give you the more naive version of their algorithm, which is, I think, easier to understand, which is not only do they figure out the like, let's take the original problem. So not only do they figure out a strategy that is that's optimal in the classical sense, and they figure out sort of the value of the game, the payoff that strategy earns, and also it figures out the support of that strategy, which essentially tells you what are the hardest rows in the matrix, the ones that are sort of tight for the minimization. Then in the second stage of the algorithm, those rows are now bound to be that value. So if you know what are the hardest rows and you bound them to be the optimal value, then now you can so the set of column strategies that gives you those values on those rows are the set of all optimal strategies.
So these are equality constraints.
These are equality constraints.
Okay.
Because it's solving it exactly.
Okay.
But again, each of those linear programs has size roughly proportional to the size of the game matrix. And we're interested in a setting where one player has a whole bunch of strategies. Go ahead.
Is there any results? I mean, so intuitively it means that the subsequent rounds are going to be much easier to solve, right? Given that you have the equality constraints.
Yeah, I guess intuitively.
Is there any way to, is it going to be formalized in terms of the actual complexity that you expect to aggregate, depending on how many equality constraints you get?
I don't think they didn't really investigate that. I mean, everything was just bounded in terms of the size of the matrix. It sounds like the worst case would be you figure out one row per stage, I guess. Yeah. Okay, but again, that algorithm is polynomial in the size of the matrix. And sometimes the game you want to solve doesn't have the property that it's a reasonable size. And towards the end of the talk, I'll give you some examples of games from reinforcement learning that have that property. But maybe to give you an example that's perhaps familiar to more of you, I think, let me talk a little bit about boosting. So boosting is an algorithm for supervised classification. And the goal of boosting is you're given a set of training examples and a set of weak hypotheses. And the goal of boosting is to find a weighted combination of the weak hypotheses that maximizes the minimum margin on your training set. And you can formulate that goal as finding a Maximin strategy in a zero-sum game. So the game is the game matrix for that game has the following shape. The rows correspond to the training examples, one for each example. The columns correspond to these weak hypotheses. And an entry in the matrix is the margin of that weak hypothesis on that example. And so you're trying to find a weighted combination, a strategy of weak hypotheses that maximizes minimum margin. That's a Maximin column strategy. And the trouble is that typically the number of weak hypotheses is very, very large. And in some formulations, it can be infinite. And so we can't just use a linear program to find an optimal strategy in this game. So this is an example of a game where it's too big for the LP solution to work. Okay. So let me talk a little bit about now existing algorithms for finding optimal strategies in very large games. So typically the assumption that you make when you're faced with this kind of situation is that you assume you have what's called a best response oracle for the player that has a very large number of strategies. And a best response oracle is the following. It's an algorithm that, for example, for the column player, if you fix a row strategy, then this oracle can tell you what is the best column strategy for that fixed row strategy. And in the boosting example that I described earlier, that oracle is just the weak learner. So if you're familiar with boosting every round, it just adjusts the weights on the examples. And for a given weighting of the examples, you find the best weak hypothesis that has the lowest error. And the algorithm that gives you that weak hypothesis is the weak learner. That's the oracle. And again, as I said, at the end of the talk, I'll describe some situations in reinforcement learning where you have exactly these kinds of games and you have an oracle for one of the players. Okay, so if you have this really wide game and you have an oracle for the column player, here's an algorithm, a pretty intuitive algorithm that finds an optimal strategy in the game. And it works as follows. So you start with, you put a uniform distribution on the rows. You find the best response, and in each round you find the best response for the current weighting of the rows using your oracle. And then you update the weights. And what is this saying? Well, this is just saying that the update of the weights puts more weight onto rows where so in each round T, you learn some best response, right? And that best response has some performance against every row strategy. And you just shift the weight onto those strategies that column strategy did poorly against. So the worse it did, the more weight it gets. And by shifting the weight in this manner, over time, you're forcing the column strategy oracle to focus on the hardest row strategies, because it puts more and more weight on the ones that it does poorly on in the past. And the analysis of this algorithm says that because of that property, over time, the minimum row of the average of all the column strategies that you generate is maximized. And this is basically AdaBoost. I've just described AdaBoost. So maybe just to help understand what this algorithm is doing, let me try to visualize how it would work against a standard game matrix. So you initialize. This is supposed to represent the weights. You initialize the weights on all the rows. And as the algorithm proceeds, it keeps generating these best responses for each weighting of the rows. And as the algorithm proceeds, more and more weight is being put on some rows. On other rows, it's decaying, going all the way to 0. And the rows that are getting all the weight are the hardest ones, the ones that are hardest to increase the value for. And so towards the end of the algorithm, the best response oracle is forced to concentrate on those rows.
Is that monotonic?
What is?
The way in which the weights increase and decrease.
No, it's not monotonic. And I'll illustrate that in a couple of slides. So the analysis of this algorithm is that if you run this weight shifting algorithm the way I described, then both the average of the row strategies and the column strategies can converge asymptotically to optimal strategies in the classical sense. And the rate is not too bad. And here, n is the number of rows in the matrix, and notice that there's no explicit dependence on the number of columns in n. As long as you have this best response oracle, there's no explicit dependence. Okay, so again, just looking at things from the perspective of the column player, I have shown, we want a lexicographic Maximin strategy for the column player. I've already shown you that the average of the column strategies generated by this no-regret algorithm, which is basically AdaBoost, converges to a Maximin strategy in the classical sense. Could it be that it also converges to a lexicographic Maximin strategy? Because that's just a special case of a classical Maximin strategy. And if that were true, then we would be really lucky and we would be done. But unfortunately, this does not hold in general. And I'm going to describe a counterexample. And I'll spend a little bit of time describing this counterexample and explaining why the algorithm fails, because that's going to motivate and explain why our algorithm is able to overcome this obstacle. So here's this matrix. So let me give you a tour of this matrix. So this matrix has 3 rows. Basically, the first 2 rows are about A. Think of A as some positive number, and epsilon is some small positive number. So the first 2 rows of the matrix are all roughly A. And on the 3rd row, you can divide the columns into 2 groups. Columns that do quite well on the 3rd row, and columns that don't. So these columns do twice as well on the 3rd row than these columns. Okay. So that's the tour of the matrix. So what if we ran our no-regret weight updating algorithm on this matrix? What would happen? So again, you initialize the row weights to uniform. And what happens initially is that the best response toggles between the first 2 columns. Now let me try to explain why that's happening. So first of all, why is it selecting columns in the first pair and not in the second pair? Well, this is happening because there's some weight on this 3rd row. And early in the algorithm, that weight is not negligible. And so since these column strategies do so much better on that third row than these do, these strategies are much better than the ones over here. And they all do about the same on the first two rows. Now, why is it toggling? Well, the reason it's toggling is that, so this maybe addresses your question. So this is sort of very typical behavior of these algorithms. At some point in the algorithm, one row has slightly more weight than the other. And notice that the way that these two columns deviate from A, from their mean, is sort of symmetric. So one is a little bit more than A and the other is not, a little bit less, and then they change places. So in this iteration, between the first two columns, it prefers the first column slightly more because it's slightly more biased towards the row that has a little bit more weight. And here, because the weight now shifts on the ones that it didn't do well, the bias just and it just flip-flops back and forth. Okay, so that's what happens initially. But now here's what happens after a while. So remember, the weight increases on the hardest rows of the matrix. The hardest rows of this matrix are the first two. In the first iterations, it's doing really well on the third row. It's 2A instead of just A. And so the weight on that row decays rapidly to 0. And pretty soon, the weight on that row is so small that basically the best response oracle is ignoring that row entirely. It's just having basically no effect on the payoff. And now it toggles between these two because the deviations here are slightly larger than the deviations here. And so as soon as the weight on that third row becomes less than basically the magnitude of this oscillation that's happening, it's going to flop over to just toggling between those last two columns, and it'll do that indefinitely. So putting this all together, if I run the no-regret algorithm on this matrix, then asymptotically it converges to a column strategy that gives the value A to every row. Whereas we know there's a lexicographic optimal strategy that gives 2A to the last row, basically just the uniform average of these first two columns. Okay, so just to sum up what I said, the basic problem is that this no-regret algorithm, the reason it works is that it shifts all the weight of these row strategies onto the hardest rows of the matrix. And that causes the best response oracle to ultimately ignore the other rows. It just focuses on the hardest rows, the ones that are hardest to maximize. Please.
There's an underlying convex optimization problem going on here. Right?
Yeah.
So that's still converging to something, but you're oscillating in I mean, that value converges to something, but the oscillation continues in these last two columns.
That's right. Yeah. The behavior of the averages are well behaved. The actual strategies themselves are not well behaved at all. In fact, people have studied the dynamics of that distribution, and it's very complicated. In fact, you mentioned Cynthia Rudin. Her thesis was on studying the dynamics of those distributions, and there's no simple answers there. It's highly complex. Go ahead.
Well, your friend had a paper about Brown motion.
Yeah.
So how does it relate to what?
Yeah. So if we look at this algorithm as a boosting algorithm, which it is, the problem that I'm describing is that the algorithm focuses too much on outliers. Right? Outliers are the ones that have small margin, and that's like sort of the fundamental problem of AdaBoost. And there's a whole family of algorithms that have been designed to try to address this problem. Brown boost is one of them. There's logit boost. There's meta boost. There's just a lot of them, and they all try to basically. So AdaBoost puts an extreme amount of weight on these outliers, and they all, one way or another, try to soften that extreme behavior to try to get it to perform better.
So in what sense? So what you propose here falls in the same family, or is it something different?
It's something different because although it's the same issue, we're taking a slightly different approach. So again, the problem is that it focuses too much on those hardest rows. It ignores the ones that aren't hardest. But in our objective, we care about those rows. So our solution, which I'm about to describe, is just to change the weight updates in such a way so that the weights do not decay all the way to 0 on those other rows. And then that'll make the algorithm not ignore them. That's the sort of outline of what we're about to do.
The analogy of lexicographic objective for boosting is compared to it's still the same worst case optimum, but this sort of less than worst case. What is the game theory?
So the analogy would be usual boosting is trying to maximize the minimum margin.
Yep.
This objective is maximizing the minimum margin, and subject to that constraint, maximize the second smallest margin,
Okay.
and then the third smallest, and so forth.
So at a high level, can you think of it as sort of you don't just care about just the support vectors, but you actually care about sort of you're stepping a little further out,
Yeah.
and you're adding these kind of soft support vectors, and you care about their margins. as well.
Yeah, soft support. That's a good phrase for it. Soft support vectors. Yeah. Or maybe even another way of thinking about it is that you care about the whole margin distribution, and you're trying to push it all up, but while maintaining the worst case property.
But the amount you care about sort of declines as you step further up.
I don't know. So it's lexicographic. So it's not that I'm putting an amount of weight on each one.
Okay,
It's
the weight
like
is just now kind of the
yeah,
method.
yeah.
So improved generalization performance.
No, not that I know. I mean, that's something I would like to study because we're working on this now.
Within the work of like Buxter and I don't remember who else, who studied actually the full distribution.
Yeah, that's right. That's right. I should mention that. Yes, people have studied how to bound generalization in terms of the entire margin distribution, but not. I don't know how to connect their work to this lexicographic property. Okay, so maybe I can. I'll try to explain our algorithm. So, okay, so before jumping into exactly what our algorithm does, let me give a little set some foundation. So, for any vector C, I want to think about the shifted version of our game matrix. So M sub C is just take each column of our game matrix and subtract the vector C from it. Okay, if you did this in MATLAB, this is what I mean, M minus C. Okay, now this shifting operation has two interesting properties. One is that our assumption that we have a best response oracle for the original matrix implies that we have a best response oracle for any shifted version of the matrix. And the proof is just this equation. The payoff of any two strategies in the shifted version is just the original payoff minus this quantity that's independent of Q. So if you can argmax this quantity, then you're also argmaxing this quantity with respect to Q. So we have a best response oracle for any shifted version of the matrix. Now here's the second fact, which is why we care about shifted matrices, which is if you let V star be sort of the vector of values, the sort of the vector of values that you're going to get for each row strategy, the vector of payoffs that you're going to get on each pure row strategy under the lexicographic optimal, then if you just shift your matrix by that vector, then any optimal strategy in the traditional sense on this shifted matrix is a lexicographic optimal strategy on the original matrix.
This requires some understanding.
Yeah.
So the vector V is now kind of if it was d-dimension, now it's sorted. So
It's sorted. That's right.
So
yeah, this is a very good point. So I decided not to put this in. I thought it was getting too much into the weeds, but I can see you're going there. So you may be concerned that. So let me just say this. So it turns out that we can assume, without loss of generality, that the first row of our matrix is the hardest one, the second row is the second hardest, and so on. And further, every lexicographic optimal strategy is already sorted.
So that means. So let me see if I follow that line. It means that if there are two optimal strategies,
That's right.
in the lexicographical sense,
Yes.
the hardest the hardness of a pure strategy is fixed, independent, right? So I cannot fix a strategy in which this will be the second hardest and this will be the fifth hardest and another one that will switch places.
That's right.
This is fixed.
That's right. So I used to have a slide in it. I think another way of what you're saying is there's an unambiguous ordering of the rows. One of them is the hardest, and the other one is another one that's the second hardest, and so on. And it's independent of the actual strategy that's being used. And that's why this kind of that's part of the reason why that fact is used to prove this lemma. I should have put this in the presentation. So now, if I just shift down all the rows of the matrix by how big those worst case values are, now any optimal strategy in the traditional sense is a lexicographic optimal strategy for the original matrix.
Equally hard.
Yes,
right?
that's right.
Any optimal strategy must be.
That's right. Okay, so combining these facts, now in order to figure out a lexicographic optimal strategy, I just have to compute this vector v star. If I've got this vector, again, then I can just run my usual no-regret algorithm on the shifted version of the matrix. And I have a best response oracle for that shifted version. I argued for that earlier. So now the problem reduces to computing this vector of values v star. Okay, so how will I do that? So here's the algorithm in pictures for how to compute v star. So I run my no-regret algorithm on my matrix M. And after a while, I get a picture that looks like this. I have a lot of weight on the hardest rows and a little weight on everything else. So I can use that fact to identify which are the hardest rows of the matrix. And here I've colored them blue. And everything else I've colored black. Now that I've identified those rows, okay, and as you pointed out, they're sort of unambiguously the hardest. They're the hardest for all strategies. Now I rerun the algorithm. But when I rerun it, every round I change the weight update a little bit. Basically, I look at my distribution that the algorithm is giving me on the rows. And if I find that the weight on the non-hardest rows is too small, which is the problem in the counterexample, right? I just rescale the weights so it's not too small.
So you kind of,
I force those weights to stay bounded.
Matrix M, or do you change the update?
Just the updates. So those weights that were decaying to 0, which was the problem, I just forced those weights not to decay to 0. I bound them away from 0. And the order is roughly 1 over epsilon to the 4th. Go ahead.
So in other work on other problems, with a similar flavor, like problems of tracking the best moving target in online learning, or maybe bandit optimization algorithms, they also have this problem of multiplicative weights going to 0.
Yeah.
And what they usually do is just mix in kind of a little bit of uniform distribution or everything and fix the problem that way.
Yeah, but that doesn't work for us.
Why not?
At least I couldn't get that to work. Because the uniform distribution sort of smears everything. So one way to think about it is that what I really want is I want my algorithm to be running, I want my no-regret algorithm to be sort of running in parallel on the hardest rows and the non-hardest rows. I want it to focus on both. And these black ones, the non-hardest ones, those weights are getting really small. And if I just mix this distribution with uniform, it's going to, there's some structure to this distribution that I want to preserve. But if I mix it with the uniform distribution, those weights are so small that it'll just get smeared. And my regret property will no longer hold. I'm not sure if this is making sense, but I need to sort of I want to run 2 versions of my no-regret algorithm on these 2 groups of rows. And I just want them to be run at different scales. But within each group, I want those proportions to be preserved so that I have the no-regret property.
So, I mean, I don't. Yeah. You have an algorithm with a proof. I have nothing. So
your idea for a first approach is the right one because that's the first thing we tried.
And then I would say, adding that little bit of uniform distribution.
Yeah.
The guys that became very small, it would make them big again.
Yeah.
The guys that are big, it wouldn't change because it would just be epsilon change to them. So the big extent, it wouldn't affect them at all. It would have the same effect of exactly amplifying the little ones while not touching the big ones.
But the trouble is that, so suppose I just cared about these non-hard rows, right? I want to maximize the smallest one of the non-hard ones, right? So what I'd really like to do is run my no regret algorithm on just those rows. Now, remember, these weights are the blue weights are on a totally different scale than the black weights. So a small number compared to the blue weights is a very big number for the black weights. So if I mix the entire strategy with the uniform distribution, even with a small mixing coefficient, that's going to be a big mixing coefficient compared to the weights on those black rows. And it'll sort of totally screw up that algorithm that's running on those rows, because sort of on their scale, I'm mixing it with a huge uniform distribution.
Make more explicit what do you mean by rescaling here, and then maybe we can get the picture of what is the difference between that and what.
Okay. Do you want to ask a question first, or should I?
Say that in general, you could propose different strategies for doing this regularization / smoothing. You can think of it as all other ways, or pruning or smoothing and so on. But your lexicographic objective, in the end, gives you a single correct way that will to do it that will maximize it. I mean, so the fact that there is there's other ways to do the smoothing / regularization are inferior, is because for lexicographic there is one of them that is the right one that maximizes it. Is that fair?
Well, I don't know. I would say it's inferior because of the algorithm we're using. There may be another algorithm. So we're solving this problem in a no regret way, and there's nothing that tells me that the no regret algorithm is the best way to solve this problem.
Okay, but there's a function of both the objective and the no regret approach. Okay.
So let me answer your question. So when I say rescale, what I mean is that I have a constant in mind, lambda, okay, and I want the sum of the black weights to always be at least lambda, and the sum of the blue weights will be at most 1 minus lambda.
How do you define that? So,
so
isn't it so? It could be that I always take the smallest one and make it lambda.
No. Yeah, you're right. So I do a differential normalization. So I look at the blue rows, and I normalize them so their sum is 1 minus lambda. And then separately, I normalize the black rows so that their sum is lambda. But within the groups, I maintain the proportions between them, and that's very important. And that's
how do you define the blacks and blues?
So in the previous step of the algorithm, I run the algorithm. I look at the places where it's putting a lot of weight.
There needs to be some threshold. It needs to be well defined, right?
That's right.
So
right.
Can
so there's a threshold that comes from the analysis that says that if the weights on certain rows are above the threshold, then I know that they should be colored blue, and if the weight is below a threshold, then they should be colored black.
Okay. So let me see if I get it right. So you say, okay, I run the algorithm, and then I set a threshold, and I make sure that all the rows that are below the threshold sums up to lambda. So I renormalize them so that they sum up to lambda.
I identify the rows first, then I start from the beginning, and in every round I ensure that the black rows are at least lambda, and the blue rows are at most 1 minus lambda. Okay.
So you said that this threshold comes out of the analysis. So what does it depend on?
The desired error. And
And the gaps.
and again.
So it looks like you're precisely choosing the active dual variables again, just like these 2006 guys did.
Yeah.
You're kind of choosing the active constraints and treating them separately from the inactive constraints.
Yeah, I guess, that's right. Yeah.
So just to make sure that I understand what you just said, is you had the initial step in which you identified the blues and the blacks.
Yeah.
And now you restart from scratch, but after every AdaBoost update, after every multiplicative update that you do, you redo
differentially normalize. I normalize one group separate from the other. And within the groups, I maintain the proportions, and that's super important. That's why the uniform mixing doesn't work for us. Because if I just uniform mix, then the black group will just get blown away. The proportions within them will be totally screwed up. Okay, so I do that. So what does this get me? So before I can explain what this gets me, let me just give you a little bit more notation. So remember this vector of payoff values. This is its definition. And so by the definition of theta, this is a sorted vector, right? The first component is smallest than the second and so on. So let's just identify the first breakpoint in that vector. So what this is saying is that the first k values of the vector are all equal, and then the k plus first one is a little bit more, right? K could be 1, k could be n, it could be anything. So if I do this scheme that I just described, identify the hardest rows, and then then start from scratch and then differentially normalize, then the minimum over the hardest rows will be v1, sort of the hardest value, smallest value. And the minimum over the non-hardest rows is going to be v star k plus 1, sort of the minimum over those rows. So it's like I was saying earlier, I'm sort of running the algorithm in parallel on these two groups, and they're each computing this value sort of separately. And the key to making this happen was that differential normalization that kept the weights on the non-hard rows from going all the way to 0. Now this means that the best response oracle can ignore those rows, and this is why I get this property. Otherwise, I would run into the problem I had with the counterexample, and this might be as small as v1. Okay, so I just showed you how to get basically v1 through vk plus 1, and this procedure that I described can sort of be iterated to recover all of the values in the entire vector.
So what you would do is to first recover the first k plus 1, and then just add them to the objective.
Yeah, subtract them. Shift them. Just shift the first rows. They're all the same value. Now they become the hardest rows. Before they were in two groups, now they'll be in the same group. That's right. And so after you sort of do all this, then the theorem that we have is that this algorithm that I just described at a high level finds this a epsilon optimal lexicographic strategy in about this much time, and which is about quadratically worse than your usual no regret algorithms. They're usually squared, and this is to the fourth.
Can you say something about how quickly your algorithm finds there's the standard minimax? Because it does.
In the same amount of time. That's basically the first. No, that's not right. That's not right.
So
No. It's slow. It'll be at the same rate. It'll be at the same rate.
Okay.
It'll be the same rate. Yeah.
Do you think that's just inevitable, or could you find the best of both everything?
I wouldn't say it's inevitable. I don't.
Okay.
Does it has, but just by the sound of it, it sounds very similar to the spectral graphs in graphs and stuff like that. Does it somehow relate?
Spectral, I'm not sure how.
So for example, that if you take a matrix and you want to find the first eigenvector of the matrix, then you can just apply the matrix over and over and over again. Just a random vector. And all the weights decay exponentially. And this is what happens here, right? You get this exponential decay of the weights and stuff like that. And you know that a lot of properties of matrices come from the gap between the first eigenvalue and the second eigenvalue. So, for example, if you ask how fast will it converge to the first eigenvector, it's just the spectral gap. And it seems as if this is exactly what's happening here, right? If the values, when will it be hard to find them when actually the gap is small, right?
The key gap is this gap right here.
Yeah, exactly. So,
but I don't know if it's related to the gap.
Either any connection? Can we tell some unified story about that, or?
I don't know. I don't know if these values are related to the eigenvalues of the matrix. I'm not. It doesn't.
Gap is in your analysis. The difference between v star k and v star k plus 1 appears in there.
It does.
Where? Okay.
Yeah, so if it's small, then you don't care, and if it's large, then.
But I don't know whether it is, or if it is, how it is connected to the eigenvalues. I'm not sure. Okay, and now, so that's our algorithm. Now I'll just briefly describe some problems in reinforcement learning that can be solved using this kind of algorithm. Okay, so what's reinforcement learning? So just let's step back. So the goal in reinforcement learning is that there's some agent navigating some unknown stochastic environment, and you're trying to come up with a control policy for that agent. So typical applications are like navigating a vehicle or guiding a robot, something like that. And the only feedback that this agent receives is some exogenous reward signal that tells it in every state of the environment whether that state is good or not good. And the goal of a control policy for the agent is to maximize the cumulative reward that the agent receives over time. And so the value of a policy is defined as the sort of total cumulative reward that the policy receives over time, and that's called the value function. I'm going a bit fast because I think maybe you guys are familiar with this. Okay. Now there's really sort of two definitions of an optimal policy, and sometimes the distinction is not made clear in papers that you read. A weakly optimal policy is one that maximizes the value for some fixed initial distribution on the states. Right? We'll call that a weakly optimal policy. And a strongly optimal policy is one that maximizes the value of the policy no matter what the initial state distribution is. So it simultaneously has maximum value at every state. We'll call that a strongly optimal policy. So weakly optimal and strongly optimal. So clearly weakly optimal strategies exist just by continuity or something. But it's not obvious that a strongly optimal policy exists, one that maximizes value at every state simultaneously. But there's a classical result that in a Markov decision process, which is the usual model for reinforcement learning, there's always a strongly optimal policy. There's a control policy that maximizes reward no matter what state you start in simultaneously. But a lot of reinforcement learning algorithms, especially the ones that do not assume that there is an explicit description of the environment, they only return a weakly optimal policy. That is, you specify some start state distribution, and it'll find the optimal policy with respect to that initial distribution, but perhaps not all states simultaneously. Those are called model-free algorithms, the ones that don't assume an explicit description of the environment. So this lexicographic optimal strategy finding algorithm that I just described to you is a way of converting a reinforcement learning algorithm that returns weakly optimal policies into one that returns strongly optimal policies in the following way. So I construct the following game matrix. The rows of the matrix correspond to states of the environment, and the columns of the matrix correspond to all possible policies. And an entry in the matrix is the value, so the ijth entry is the value of the jth policy when you start at state I. And it's easy to show that the lexicographic Maximin strategy in this game is a strongly optimal policy. It's maximizing the value at every state simultaneously. There could be, yeah. Well, probably it's just for technical reasons, it might be better to assume that there's not, because that implies that there might be infinitely many actions, and that gets hairy. But there's certainly exponentially many rows. Exponential.
The bandit case to make it just more conventional. Would the same analysis hold so far?
If you reduce the bandit case, you would have one arm per policy,
yeah.
But there would be exponentially many arms, exponential in the number of states. Yeah. So a strongly optimal policy is a lexicographic Maximin strategy in this game. And what is a best response oracle for this game? Well, it's an algorithm for computing a weakly optimal policy. You fix some distribution on the states, and the best response is the optimal policy for that fixed input distribution. Okay, so I've given you a reduction. And I'm a little hesitant to say this because it seems a little surprising, but so far as I know, no one has actually given this kind of reduction before, going from an algorithm that computes weakly optimal to strongly optimal. But let me add an asterisk to that because it just seems kind of too good to be true.
So again, so where does the lexicographic stuff come in? So why doesn't standard boosting do this weak to strong thing that you're suggesting?
So what boosting would do is that it would return a policy that has the highest value on the start state that is sort of the worst start state to be in. That's what standard boosting would give you. And this gives you the highest value on all of them simultaneously. Okay, so that's application number 1. Application number 2 is perhaps maybe a little bit more obvious. So in a lot of environments, there's not just one natural value function that tells you the value of the policy, there's like several. So if you're driving a car, there's like multiple objectives you're trying to satisfy. You're trying to go as fast as you can, you're trying to avoid crashes, you're trying to stay on the road, etc. And these folks gave an algorithm for finding a policy that lexicographically maximizes all of those, that set of value functions, but assuming a fixed ordering on the value functions. So they assume that as input to the algorithm that one of the values is, one of the objectives, like say speed, is the most important. And then another objective, like staying on the road, is second most important, and so on. So you're given that ordering, and they find the one that's best with respect to that ordering, lexicographically best with respect to that fixed ordering. If you were to apply our algorithm to this problem, where the game matrix is defined as follows, again, the columns are the policies, and now the rows are the different value functions. And the ith jth entry is the value of the jth policy with respect to the ith value function. A lexicographic Maximin strategy for this game is a policy that it does the same thing. It finds the lexicographically best policy, but without having to specify which value functions are more important than the others.
But then they need to be, all the evaluations need to be in the same scale.
That's exactly right. That's exactly right. I was just about to say that. If this assumes implicitly that these things are on the same scale. If they're on different scales, then the different scales are implicitly telling you which is more important than the other. That's totally right. Okay, and that's it. It was just a very sort of brief tour of the application. So again, I gave you an efficient algorithm for computing these mistake exploiting strategies and in very large games and a few applications to reinforcement learning. So thanks a lot for your time.
Does anyone have questions?
I'm curious if you've tried this on real problems.
So we have a sort of toy simulator, a car driving simulator, and we tried it on that. And you can definitely set up a situation where, and we give it like multiple objectives, you know. And it's quite easy to set up a situation where a traditional algorithm is not going to be maximizing all objectives simultaneously in ours.
So don't crash. Stay on what else?
Stay on the road, drive as fast as you can, don't crash.
Those sort of equally weighted, right?
Yeah, they're all on similar scales. That's right.
I have a question I want to address. So I think what Chris said in the beginning of the talk interests me about what happens if I don't want a strict lexicographic order, but I'm saying, you know, I'm willing to sacrifice something with respect to this max guy. So I mean, maybe I won't be optimal with respect to the best thing, but then, you know, if I can be much better on the second best and so on. And I think an equivalent way of saying this is to say that I have some model of how my opponent chooses his strategy. Perhaps he can sort them from the best to the worst, but rather than picking the best thing, maybe he has like a stupidity coin, and he flips it, and he, you know, am I going to choose the first one, yes or no? Flips the coin. If it, you know, if it's heads, I choose that one. If not, I move on to the second one and I flip again. I think that's maybe equivalent to what I want to say about, you know, let's say the parameter of the coin is no. But it doesn't have to be that. Just let's think of the more general thing that Chris was suggesting. I just want to somehow be more soft with respect to the first one. So it's a soft lexicographic. And it seems that the algorithm from 2006, I forget the authors, the recurring LP one, is easily adaptable to that setting. Whereas, so maybe I'm missing something here, but it seems like rather than outputting a set of, you know, of equality constraints, the constraints you pass on to the next step will be, rather than a set of linear constraints, namely a linear subspace, you would just have some set of inequalities which encode a hyperslab, which says that, you know, you have to be roughly in this optimal space, but there's some epsilon. And of course, you move away from the space, you get worse with respect to the first one, but now forget about that. Focus on the second.
That sounds right to me.
Well, the same question as Lynn had about the convex, if you know what the combination is, and we have some sort of distribution over...
But here I don't assume I know anything. I'm just saying I'm willing to pay epsilon on the first objective, right? I don't, or let's say they're.
But it implicitly assumes that you have either some class structure that you can go back to defining.
Yes, I think it's equivalent to saying the coin flipping thing, with the p-skip type of thinking. But my question is, okay, so now I think we understand how to take the simple recurring LP algorithm and make it softer with respect to kind of the important decisions.
Yeah.
How do you take your algorithm? This is kind of a, I don't know.
I don't know. That's an excellent question. And the answer is I don't think that this algorithm is suited for the kind of extension that you're describing.
But why? It seems that...
Isn't it like going from, so, you know, we had all these algorithm version space type of algorithm like halving and stuff like that, going from this class of algorithm to algorithm that work with posteriors. So basically what you say, if I have a policy now, I measure it with respect to the worst case, and I kind of penalize it based on how far it is from the best policy, as opposed to kind of the version space thing that will just cut out everything which is non-optimal. Here I'm just going to penalize it in some way and then proceed. So I at every step I have some sort of kind of aggregate the penalties that this policy gets. But again, the question I can see, how can you need to have some sort of model. So you propose this coin toss model. Then I think about this model that it does not assume anything about the opponent. You don't have to assume that the opponent.
I'm assuming the opponent is p-stupid. So it doesn't. I don't want to just exploit his mistakes. I'm assuming he will make mistakes with a probability that I know. So
yeah. So I mean, so let me try to answer your question more fully. So one thing you might guess is, so there's this. I define this term lambda, right? So you're normalizing these two groups of rows differently. One of them is at least lambda, and the other is at most 1 minus lambda. So you might think that to make things more softer, you change the value of lambda somehow, right?
Yes.
But the thing is that whatever lambda is, if it's more than 0, then if you run the algorithm forever, it will end up in the same place. It doesn't matter. As long as lambda is more than 0, then it ends up in exactly the same place. It just changes how long it takes to get there. And so the lambda is tuned to make this for speed, to make the convergence time as good as possible. But it doesn't affect where the algorithm ends up. So that's an idea to address what you're saying. That won't work, and I guess I don't have another idea on the top of my head. Yeah.
Good answer. No more questions? Thank you. Very good.